Hi everyone, and we're going to be talking about inflation this week. Where does the idea come from? What is its historical motivation? And what are our best ideas regarding what happened in the earliest moments of the universe? But before we get started, I just wanted to say that by and large, inflation is separate from the big part of the Big Bang Theory. And there are various models that we'll explore in a little bit of detail, not so much in this presentation, but in the discussion post for this week. But um, by and large, they all agree on the heart of the Big Bang Theory. So I just wanted to point that out before. This is an interesting thing, I think, that's important for people of faith to reflect upon. Here's a nice quote from Paul Davies in The Cosmic Jackpot, where he writes, "At the level of popular Sunday school Christianity, God is portrayed simplistically as a sort of cosmic magician, conjuring the world into being from nothing and from time to time working miracles to fix problems. Such a being is obviously in flagrant contradiction to the scientific view of the world. The God of scholarly theology, by contrast, is cast in the role of a wise cosmic architect, whose existence is manifested through the rational order of the cosmos, an order that is in fact revealed by science. That sort of God is largely immune to scientific attack." And so I think that's certainly an interesting perspective that he has. And so there are this idea, and part of what leads to perhaps Paul Davies' perspective is the notion of fine-tuning that we're going to talk a little bit about, and why we certainly would need to be careful and in terms of using that, because I think there really is a big language barrier between what it means when a physicist uses that phrase and then what it means in popular culture. But we'll get to that a bit later. But first of all, the classic inflation paradigm was something that there were three problems, and I put them in quotes here because we're not actually sure if these are problems just yet, and I'll explain why, especially the first one. But there's the so-called monopole problem, the flatness problem, the horizon problem. This was part of the original motivation, and the interesting thing about inflation is that while these might not necessarily be problems, inflation actually helps explain some things about our universe in a very successful way. So here's the essence of the monopole problem. Basically, if there was some kind of phase transition that occurred, you would get the formation of all kinds of different exotic particles, and one of them would be monopoles, which we don't presently see. There's an example of breaking a magnet in half, and if you do that, the atoms will rearrange such that you'll end up with a north and a south end. You won't just get a magnet that has just a north end and a magnet that has just a south end. That happens when we break magnets. However, in the early universe, if there was some kind of symmetry due to grand unification, which we're not sure if that's the best idea of the early universe, it's a promising approach. But basically, we're not sure if there even should be monopoles in the first place. But if this was the case, why don't we see them if there was some kind of grand symmetry that's broken? And so one of the solutions of inflation is that inflation would help dilute the density, that it would be so small that we would basically never measure them in the present day universe. Now, of course, one might just argue that, well, we don't see monopoles because there aren't any, which is a perfectly good argument at present. Maybe that won't be a good argument if we have a more comprehensive theory. And really, this problem only exists if there was any grand symmetry in the universe. But as I've noted here, all searches for such grand symmetry, mostly via proton decay, have turned out negative. But then even if that did occur, we're not even sure necessarily if that would create monopoles. It's a possibility in certain frameworks of the early universe. So this might not even really be a problem. So it seems a little silly to have a field that solves a problem that we're not sure if it's a problem. But if it is, then inflation actually does help answer the monopole problem. We're not sure yet. And here's, of course, a funny comment from one cosmologist, Martin Rees. Quote, "Skeptics about exotic physics might not be hugely impressed by a theoretical argument to explain the absence of particles that they themselves are only hypothetical. Preventative medicine can readily seem 100% effective against a disease that doesn't exist." And so that might be the case of the monopole problem, but it might be a real problem. We just don't know yet. But it's interesting that this was some of the early motivation for inflation. Um, and the next one is the flatness problem. So here is Alexander Friedman. The Friedman equations are back, and you can rewrite them a different way than we have previously. Basically, the idea is this. if the universe is approximately flat today, it must have been much more flat in the past. And so how flat is it today? If you go ahead and if you look at the bottom, you find that the fractional energy density of stuff is approximately equal to 1. And it's flat to at least less than 1 part in 100. But the problem is this. So mathematically speaking, you can actually calculate, here's a little formula at the bottom, where you can calculate what the total fractional energy density is as a function of time. And it turns out that it would change substantially as the universe gets smaller and smaller and smaller. So you see some things in that equation. There's omega m, that's the density of matter, and then you have the fractional energy density of photons, that's the next term, and then so on and so forth. And then you also have A, that's the scale factor, again, the scale factor of the universe, and then A naught is the present day scale factor, which typically equals 1. So basically, you can calculate this would be back into the past, and you find, and you can simplify that equation and rearrange it a little bit, and you find that at the time of a high redshift value, like for example, in the era of Big Bang nucleosynthesis, the universe would not have been flat to 1 part in 100, but it would have been flat to 1 part in 10 trillion. And then you could go back even farther to the Planck scale, the earliest possible time of our universe, and find that the universe was flat to 1 part in 10 to the 57th power. And so what does this mean then? It means that in terms of the critical energy density of the universe, the actual stuff in the universe is extremely close to this. And again, if the universe is approximately flat today, it must have been much more flat in the past. So here's an example of adding or taking away a grain of sand, a nice little plot about 1 nanosecond after our universe began. So the green line is taking away a grain of sand, and if you had done that a nanosecond after the Big Bang, from the overall density of the universe, we would presently be experiencing a much more accelerated expansion, and we'd be closer to the so-called Big Rip. But if you added a grain of sand, the entire universe would have collapsed by now. That's the curve in red when you add a single grain of sand to the universe. And so basically it seems as if the universe was really, really close to the critical density. And if it wasn't, then the universe would be quite different from how we see it today. So is this really a problem? A nice summary from a few quotes here. This tiny value is the crux of the flatness problem. If the initial density of the universe could take any value, it would seem extremely surprising to find it so finely tuned to the critical value. But here's the problem, and this is a nice quote from another cosmologist, Sabine Hossenfelder. Apologies if I messed up your name. Whenever someone talks about the likelihood or probability, you should ask, quote, what's the probability distribution and where does it come from? And so really the flatness problem comes from if you could assume the density could take any value, then it would be really surprising, and it has to be finely tuned within this possible range. But the problem is this, that implies that you know what values it could actually take. That's the problem in all of this. So that's a good question in terms of talking about fine-tuning, to be able to define what's the probability distribution, where does it come from, and how many chances, how many times have we played this game? You could even get into that question. And so at first glance, really it's not so surprising that something that increases in time was much smaller than the past. It's kind of like the cosmological constant. It's just something we measure, and that's that. But for example, there is kind of this bias towards beauty. Whenever numbers are closer to 1 or 0, that's particularly beautiful, but 10 to the negative 57th is rather unpleasant. It's like, well, I don't think that it really makes any sense for my initial conditions to be flat to 1 part in 10 to the negative 57th. But at the same time, that implies you know what the probability distribution is. But anyways, let's say that it is a problem, and how would inflation help? Well, let's first pause and take a look at this question here. And this is, again, part of the problem about initial probability distributions. Here's another nice example from Sabine. Imagine you just hatched from an egg and don't know anything about astrophysics. And then you look at the solar system for the first time and you find that the planetary orbits almost lie in exactly the same plane, and that to you, that seems so incredibly improbable that it is something that demands an explanation, because you could imagine that well, all of the planets just simply started off in random distributions, and they could have taken on any possible path, but yet they ended up taking on and all aligning in approximately the same plane. Now, again, if you assume a uniform probability distribution, this would be incredibly unlikely. But then you could say, get even better and say, well, hey, maybe there's this field that brought them all into the same plane, and then the field decayed, so we can't measurement. Now, where's my Nobel Prize? Which is how some people think of inflation. If this is the main motivation for inflation, that is probably how we should think of it. But it turns out inflation is a lot more robust than just simply explaining why the universe is so flat, or the lack of monopoles when we don't even know if there should be monopoles in the first place. But here's a nice example of having a good idea of what the initial probability distribution would be. And here's an example of a number of other solar systems, and you find that they all look very similar, including mini protodisks. So these are solar systems that haven't formed nice planetary rings where planets are traveling in ellipses around. Basically, you have a big a flat array of dust, that there's been some kind of initial collapse of your central star, and then you see the formation of protoplanets around that star. And you find that whenever solar systems are forming, they tend to align due to some other types of physics. And so, anyways, inflation would help. Basically, inflation takes whatever the initial value is and shrink it by a factor of 100 orders of magnitude. And that would be great if you started with initial value like close to 1. But here's something that's kind of silly, because what if you started with a um, uh, really clumpy universe, a universe that really wasn't that flat, or just the density was way bigger than what would be required for flatness. So if you started with a really big initial value, then inflation wouldn't really help you. So this is the problem, basically, that inflation doesn't solve the flatness problem, because we don't actually know if there's a flatness problem or not, because we don't know what kinds of initial values our universe could have taken. So this leads us next to the so-called horizon problem, which is a really interesting problem, and it might not be really a problem, but we want to explain everything that we possibly can. The horizon problem essentially stems from this, that the cosmic microwave background has pretty much the same temperature in all directions. And then if you trace back the origin of that, you go back far enough, you would find a very interesting thing. This graph on the right summarizes that, where you would go ahead and look at the distance between parts of the cosmic microwave background and find that they are actually farther than light could have traveled since the beginning of the universe. So this basically leaves us with some kind of problem in terms of explaining this uniform temperature, and that it's easy to explain uniform temperature if you have two, say for example, you had two chambers and they were in some kind of causal contact with one another. However, what would happen if you have two chambers that are the same temperature, but there hasn't been enough time for them to communicate with each other to come to some kind of thermal equilibrium? And that's essentially the essence of the horizon problem. It's an interesting question that inflation actually does help with, but it really boils down to asking why this initial condition. Why did the early universe have a uniform temperature? It's not really a complicated thing to have an initial condition of a uniform temperature, and you might think that physicists might not think that needs explaining, but it's something that we wanted to explain in the early formulations of inflation. So here is how inflation helps. Um, if you go ahead and ask, well, how could parts of the early universe be in causal contact with one another? Well, it turns out that they actually were, and they had time to come to some kind of thermal equilibrium. But then the universe expanded really rapidly, and you see here that in a short amount of time, spots in the universe would have been separated from each other, and then that leads to what we see today, where the distance between cosmic microwave background spots is bigger than the distance traveled by light. And so essentially that makes this problem go away, because that explains how you can have the universe being a uniform temperature, but at the same time not having enough time for the light to have traveled the effective distance of between spots in the early universe. However, in terms of initial conditions, inflation doesn't really help with this either. It doesn't answer why this initial condition, because inflation itself requires an initial condition. And then if you go back far enough in time, without inflation, you would reach the era of quantum gravity. And so a great question is, what do we know about the likelihood of initial conditions in the regime of quantum gravity? And the answer is nothing. And so really, maybe there's some kind of effect that we could think about in the early universe that explains why the temperature is homogeneous. Without inflation, you wouldn't necessarily need inflation. Inflation can help with that, but what we really need is an adequate model of quantum gravity, which we don't yet have. So, anyways, that's a takeaway with that, but inflation actually might be onto something. So yes, the beginning of this was a little critical in the sense that, well, the monopole problem might be a problem, but we don't know. And the flatness problem, well, does it need explaining? If the explanation itself needs explaining, and is this even a problem? We don't know, because we don't know the initial probability distributions of really of any of this. Or the horizon problem. That is another interesting thing. But it turns out that inflation was good for something really, really, really important about our universe, that it provides a mechanism for structure formation. Because if you have some kind of quantum vacuum fluctuations, they would rapidly appear and disappear. But if you had a period of rapid inflation, you could, in some sense, freeze them in place and provide the seeds for early galaxies. And this is a really, really interesting thing about the cosmic microwave background, where the horizon problem stems from thinking about how uniform it is, but it's not perfectly uniform. So where do these anisotropies come from? Well, here, if you are not going to amazed by this, I don't know how to help you. But there were a series of remarkable predictions, and here's three of them. I'll explain these in a slightly different way. But the first one is cosmological perturbations spend time outside the Hubble radius. Amazing. This implies the disappearance of the decaying mode and the presence of coherent oscillations in the cosmic microwave background power spectrum. Again, really amazing. Or the fact that the 2-point correlation function of the inflationary fluctuations should be close to scale invariance. Also amazing. So I hope that these are a number of predictions that came after inflation. So this is a really important thing, because at one point we didn't know there were any kind of anisotropies in the cosmic microwave background. We didn't have the cosmic microwave background power spectrum, and a number of predictions were made. If inflation is true, this is what we should then measure. And then we went and measured these things in the cosmic microwave background. That is a really significant thing in terms of even very precise types of variations from this. Here's we're going to come back to these two in particular, and this is again really important. The first discovery of these anisotropies in the cosmic microwave background, they were predicted by models of inflation, and they were discovered and measured for the first time in 1992. And in 3 decades since then, approximately, really the results have just gotten better. These results have been consistent with predictions of a particular type of inflation, a single field slow roll inflation with a minimal kinetic term, which I'll unpack that a little bit here. And this is important. These are predictions, not postdictions, in the sense that, well, here's this data, how can I build a model to fit the data? No, this is here's a model, and I'm going to make some predictions about what we should find, and then I go and find them. That is really, really exciting and significant. So regardless of any kind of motivation for inflation and whether those are really problems or not, this is really exciting. And in the third bullet point, this one again we'll come back to just in a few minutes, but this is that the scalar spectral index should be close to but not equal to 1. And here's an example of a measurement of it from some of the most recent data, Planck data, where the scalar spectral index in S equals 0.9645 plus or minus 0.0049, which means that this is less than but not equal to 1 at more than 5 sigma, which is giving us a lot of confidence that these models of inflation are onto something. So some challenges and interesting things with this is that there are some problems. One is that how does one get the various parameters of inflation to match the anisotropies. So while it does predict them, how do you get it to describe the actual values? Now this leads into some more interesting questions regarding model building and the initial conditions of inflation, which is a challenging thing to do in terms of figuring out the initial conditions of inflation. Another interesting thing is that how do you stop inflation once it starts? Um, and that really was a hot topic, and the theory of reheating is basically explained that, and that's not really a big question anymore. But beyond the simple types of inflation fields, there's really a large zoo of models. And that is one of the problems that inflationary cosmology presently has, because in the formulation of inflation, there's a lot we don't know about the field. And so it is a little problematic in terms of trying to figure out, well, what parameters should I put into this? If you have so many parameters that you can describe everything, is that really a good model at all? But thankfully, some of these models make different predictions than simple or single field slow roll inflation. Inflation can also be eternal, and if it is eternal, and that's coupled to the string theory landscape that we'll get into in the next lecture, then you end up with a multiverse, which is a really interesting question. And so how should we think about this field? Well, this is where it stems and comes out of the background of particle physics. And so how does one even write this field? Well, here's a little bit of the background, where at high energies, if we want to describe how something works, the best way is to talk about field theory. And some simple examples of fields, there are of course vector fields that you have, and those have a value at every point in space and a direction. An example could be like the wind. The wind has a value at every point in space, and it also has a direction. Or you could have ocean currents or things like that. But they're also what are called scalar fields. And they have a value at every point in space, but they don't have a direction. An example could be temperature. If you think about a temperature distribution in a room outside of a light source or something like that, well, the temperature will be hotter there, but it doesn't really have a direction that it's pointing. It's just that every point in space has a defined temperature. You can also have humidity, and inflation would be a scalar field. And so you can go ahead and write the energy and the pressure like this. So there's the energy density here that's proportional to, you see this little symbol here. This is a phi squared, but there's a dot above it, which means the first derivative of that. And that's really related to a kinetic energy term. Kinetic energy essentially is how fast, in the traditional classical sense, is how fast you're moving in a particular direction squared. And then there's another term here, which is V, which is the potential term. And it turns out that if you add up the kinetic energy term and the potential term, that is related to the total energy. And then, but you could also describe the overall pressure of this particular field, where now it's instead the kinetic energy minus the potential energy. So there's a little difference between the two, and you could write them in this particular manner. So this is a good first guess in terms of how to describe this field. Why is it a good guess? Because if you have a big initial kinetic energy term, i.e. your universe is expanding really, really largely, then the first term will dominate. But if that term is small, then the second term will dominate. And that ends up with a really, really important thing, where if you have the potential energy dominating, you end up with a very high, of course, energy density. That's the top equation. But the bottom equation is really negative if the potential energy is much bigger than the kinetic. And so basically, what does it mean to have negative pressure? Well, that's how you end up with inflation. So it's a really high energy density field that effectively has a negative pressure and would press space outwards very, very rapidly. And so this is a really good guess of what that equation looks like. And then what does this do to the universe over time? Well, you can plug it into the Friedmann equation to figure out what it does over time. That's the top equation right there. And then you can also plug it into the Klein-Gordman equations. And here's a plot of this potential as a function of the scalar fields. And so it's a really interesting thing. The challenge is what kind of potential ends up working. And so experimental constraints are really important, because if you go back to the previous equation, we really don't know the form of the potential term. What is the potential of this inflation field? We're not quite sure, but thankfully we can describe the physics outside of what the potential is really well. We can make measurements and put constraints on what kinds of potentials work. And so how do you end inflation? This is something I mentioned just a little bit before, and this would be really, really complicated to do from a particle physics standpoint. And that's because what happens to this massive energy density of the inflation field? Well, it decays into the particles of the standard model. That's where those particles come from. Where did all of that energy come from that is in the field of particles? It came from the inflation field, which is a really exciting part of the early universe. But to describe how that's done, you'd have to describe how the scalar field interacts with other scalar fields, like gauge bosons and the fermions and so on and so forth. And that would be really, really, really complicated. Thankfully, cosmology gives us a much simpler approach that boils down to measuring a single quantity, which is effectively what's called the optical depth. And so that's remarkable that this entire process just simply comes down to a single quantity in terms of how inflation ends. And so that's, I'll go ahead and leave a link to a paper in the description that you can go ahead and look at this in more detail. It is fairly complex, and this is certainly not easy to do early universe cosmology, and I hope that you can get an appreciation for what really goes into this and the types of things that you would need to account for, and experimental constraints and predictions and measurements and so on and so forth. That's really exciting, but it's not easy to do this. And so here's an example of another thing that you can do and ask is, well, how did you generate? Because this is the bread and butter, really, of inflation, or at least one of the aspects of it, which is inflation generates the anisotropies in the cosmic microwave background. So how does it do that? Well, that would have to be accounted for within models of inflation. And in the cosmic microwave background itself, if you ask how small were these derivations, they were small to about 1 part in 10,000. And so during the time of inflation, they would have been much, much smaller than that. And so how do you describe this how do you describe such cosmological or gravitational perturbations within inflationary cosmology? Well, you would have to use what are called the perturbed Einstein equations. It looks something like that. And here's a very interesting thing that results from this type of concept, where if you go ahead and ask what's the overall density of this particular effect, you end up with this equation here that's on the top. And so the amplitude of these little perturbations in the early universe are proportional on the strength of gravity. That's obvious, but it also depends on a particularly interesting parameter. So there's the Planck mass on the bottom, and there is the Hubble parameter on top, which is effectively relating how strong gravity is in that era. And then there's this little term on the bottom that is a really, really important term, which is epsilon 1. And there's a little asterisk next to it, which I'm not going to get into. But the really, really important thing about this is that this equation is what's called scale invariant. And that is the power spectrum predicted of these gravitational cosmological perturbations is nearly independent of scale. And so that is a really, really important thing in the early universe. And so it's a fairly complicated thing, so I've left a little link there, and I encourage you, if you want to learn more about the cosmic microwave background's power spectrum, it would look something, there's a really nice presentation there that you can go ahead and walk through. And so what does this mean? Well, here's where the scalar spectral index comes back into play, and this is really ultimately where it comes from, that there are these predictions in terms of how big it should be, and this is essentially why it should be close to 1, because these terms, epsilon 1 and epsilon 2, are perturbation terms. They're really small. So that's why this should be close to 1, but not exactly equal to 1. And so, as a result, it's pretty cool that you can go ahead and constrain this. Here's an example of an experimental constraint here, where there's the primordial tilt, or the scalar spectral index, on the x-axis, and then the y-axis is something that's really interesting that's related to primordial gravitational waves. And so we find that all of these different measurements are most consistent with a scalar spectral index that's close to but not equal to 1. You find that all of the results there don't get close to 1. And that's a really, really important thing. That tells us that something, even if it wasn't an inflation event itself, something like inflation caused these small perturbations in the scalar spectral index. And that's a really important thing. And we'd be able to refine these even better if we're able to measure primordial gravitational waves, which is, of course, the thing that the BICEP team, I think in 2014, almost won a Nobel Prize over until we figured out that they were measuring just cosmic dust. And so that'd be really exciting if we're able to measure that. And how does that relate to constraining models of inflation? Well, if you look here, there's a bunch of lines, if you will. There's the blue line, the orange line, it says, and then there's the ones that talk about the potential term is proportional to the scalar field cubed, and then so on and so forth. There's different types of potentials there. And you find that the more we constrain them, we can rule out certain types of inflation fields. And that's a really important thing. We find that really the ones that are most consistent with the data are the simplest types of inflation fields. So this is pretty exciting, I think. And then an interesting question is, well, what about the initial conditions? Well, this is a challenge because inflation, and part of the motivations for it is that it was essentially invented to help solve a few fine-tuning problems. But then if inflation itself is fine-tuned, then you really just push the block back one more time. But what does it even mean for something to be finely tuned? It depends on the initial conditions, and that's generally all that it's talking about. Basically, the idea is this. Out of all the possible initial conditions, the initial conditions that we have occupy a small volume of the probability space that they could have. But that implies that we know what kinds of probabilities you could even have. And it also implies you know what kinds of initial conditions are natural versus unnatural. And so that is one of the challenges with all fine-tuning arguments or discussions, and that is that we don't really know, we don't really have a good grasp on what kinds of initial conditions are natural versus unnatural for many of these things in cosmology. We know things, for example, like conditions that are natural versus unnatural. If you think about the distribution of air inside of a room, because we know a lot of the background physics, we know that it would be natural to find the air evenly distributed in a particular room. But we know that it would be really unnatural to find all of the air in a room contained in a tiny cubic meter in the upper left-hand corner of the room. And so if we found a room with air in that kind of initial condition, we would be able to say with confidence that that is an unnatural initial condition. And that needs some kind of explaining how the air ended up there. But, of course, we don't know that for inflation. We don't know that for the flatness of the universe. We don't know any of these things. So you can't really do that whenever we discuss inflation and fine-tuning. They're really kind of useless types of discussions to have. And they are also for the fundamental constants, where we might talk about, well, the dark energy density is finely tuned. If it was so much different, then life as we know it wouldn't exist. We could say yes, which is part of what we can model, but you don't know what is the actual probability distribution. It might be really common that you get dark energy distributions like our universe. That's an interesting thing that we could try to model, which has been done here with inflation. So it looks like I'm missing the rest of this presentation. Okay. Well, I guess we'll stop here for now, and I'll go ahead and submit a link to the paper that discusses fine-tuning and different models of inflation, and basically the models of inflation that are preferred, the ones that more accurately describe our universe are those that are less finely tuned. And so that's why, as we come to get a better feel for what the conditions of the early universe are, we want to be careful about discussing fine-tuning in light of these. This is still a remarkable and awesome type of thing, but in terms of it being so specifically precise that it points towards evidence of God or not God, I think those types of arguments you can't really make them because we just don't simply know enough to make them. But that's just a broad overview of basic inflationary cosmology and where it comes from, what are some of the successes. It's pretty complex, but there are a few takeaways in terms of some evidences for inflation, including the anisotropies of the cosmic microwave background and the scalar spectral index are really two of the um, most convincing or most substantial pieces of evidence for this. So even if there wasn't inflation, there was something inflation-like. And if there's something inflation-like, it just also happens to solve problems that we're not quite sure if they really are problems because we don't know the initial probability distributions for our universe regarding its overall density relative to the critical density, or regarding the monopole question, or regarding the horizon question with uniform temperatures. Because just like the analogy with a room, well, you wouldn't be really surprised to find the air or the temperature in a room to be uniformly distributed. And so maybe that's the case with the early universe, but it's not quite that simple, and really we probably need some kind of adequate theory of quantum gravity. So until then, we might not know the answers to some of these questions.